Lighthouse Scientific Education presents a lecture in the mole series. The topic, molarity, molality, and mole fraction. The lecture is set up so that the three subtopics can be viewed together or individually as needed. Material in this lecture relies on an understanding of the previous lectures, atomic mass and molecular weight, and percent composition. The discussion of these important concentration scales begins with an introduction to the concept of concentration. Concentration is covered more in depth in its own lecture in the water and solution series of lectures, but is brought up here as a support for concentration scales that use the mole. Some basic definitions are offered, along with an introduction of the three mole-based scales covered in the lecture. The first scale is the most common of all three, and it is called molarity. A setup of steps and examples are offered to outline basic calculations with this scale. Molarity is also used as a conversion factor. That too will be reviewed. The second scale is molality. Steps and examples of basic calculations are provided. Molality can also be used as a conversion factor. The last scale, and the least common, is a mole fraction. Basic calculations will be presented with this scale. Concentration, and we will limit the discussion to concentration in liquids. Some compounds dissolve in liquids and form solutions. Important terminology includes the solute. That is a compound which is dissolved in the solution. The dissolving liquid is called the solvent. Together, solute and solvent are a solution. The lecture on concentrations and dilutions in the water and solution series covers these terms more in depth. The amount of solute per volume of solution is called the concentration. Sometimes, instead of volume of solution, it is amount of solvent. There are many different concentration scales. The ones of interest in this lecture have the amount of solute given in moles. There are three common concentration scales that fit this description. The first is molarity. As a unit, it is capital M. Molarity is defined as the number of moles of solute dissolved in 1 liter of solution. Capital M, therefore, stands for moles per liter. A similar scale is molality. As a unit, it is smaller case m. Molality is defined as the number of moles of solute per kilogram of solvent. Small case m therefore stands for moles per kilogram. The difference between molarity and molality is that the first one uses volume of the entire solution, and the second one only considers the mass of the solvent. Both scales have their place. The last scale is mole fraction. It is given the unit chi. That's a Greek letter that looks like a fancy X. The definition of mole fraction is moles of solute over total moles of solution. It is indeed a fraction with part over the whole. We will discuss each in turn, beginning with molarity. That is the number of moles of solute dissolved in 1 liter of solution, moles per liter. Written as an equation, the moles of solute is in the numerator and the liters of solution is in the denominator. Normally, division of the numerical values attached to the moles of solute and the liters of solution is done, so that there is only one numerical value assigned to molarity. That means the denominator becomes 1 liter. This will become clear when we get to molarity calculations. To familiarize ourselves with this scale, consider 1.5 m NaCl. First of all, when actually using the scale, it is not referred to as M or capital M. In a concentration, M is called molar. So the proper way to call this concentration is 1.5 molar NaCl. Applying the definition of molarity, 1.5 molar NaCl is 1.5 moles of NaCl in 1 liter of solution. That holds even if there isn't a whole liter of solution. The scale is the proportion of moles of solute to volume of solution. So, half a liter or 0.05 liters of 1.5 molar NaCl will only have half as much NaCl. Dividing 0.75 by 0.5 will get that 1.5. Here's 3.0 molar NaCl. By definition, it is 3.0 moles of NaCl in 1 liter of solution. Half a liter of this solution would have half as much solute. 1.5 divided by 0.5 gives 3. Concentration is proportion, not absolute amounts. One more point to bring up before moving into calculating the molarity. A solution can have more than one solute. Each solute will have its own molarity. Each solute will use just the value of its own moles in the calculation. They will all share the volume of solution. Calculating molarity is an essential skill in the study of chemistry. It is not one of the more difficult calculations, as can be seen with the 3 basic steps. Begin by calculating moles. Convert mass values of solute into moles. That usually involves molecular or formula weights as conversion factors. The second step is to get the volume of solution in liters. Sometimes the volume is given in milliliters or even mass. Use your conversion skills to get those values into liters. Finally, divide moles from step 1 by volume from step 2. That'll do it. All right, let's put these steps to work with a couple example problems. Example 1. 2.19 grams of NaCl dissolve in water to make a 750.0 ml solution. What is the molarity? Step 1 has us calculate the moles of solute. But which substance is the solute? Is it the NaCl or is it the water? If we revisit the definition of solute and solvent, we find that the dissolved component is called the solute, and the dissolving liquid is called the solvent. From the problem, it can be seen that the NaCl is dissolved solute. It is dissolved in water, solvent. Notice that the problem does not say that there are 750 mils of water. It says that there are 750 mils of solution. The actual amount of water will be less since the salt is also taking up volume. Be sure to keep solution and solvent straight. So, it is the solute NaCl that needs to be converted into moles. And there are 2.19 grams of it. Converting grams into moles requires a molecular or formula weight of the compound. At this point, the student should be relatively comfortable with getting such values, so we will skip the calculation and just use the value. Inserting the formula weight of sodium chloride into this equation with an orientation that allows grams of NaCl to cancel will produce a mole value of 0.0375. Step 2 is to get the volume of solution in liters. Currently, it is in milliliters. The conversion into liters is one that many students can do in their heads. We will use a metric conversion factor that relates mils to liters and has an orientation that allows mils to cancel. The math produces 0.750 liters. The last step is to divide the mole value obtained in step 1 by the volume value obtained in step 2. 0.0375 moles of NaCl divided by 0.750 liters of solution. The molarity of NaCl is 0.050 molar. A check of sig figs in the problem verifies that having 3 sig figs, 500, in the molarity is correct. That's the process. The second example asks, what's the molarity of a solution prepared by mixing 6.07 grams of potassium nitrate, KNO3, in water to a volume of 240 mils? The wording "to a volume" is there to tell us that the water is added until the entire solution has a volume of 240 mils. Returning to the definition of solute and solvent and reviewing the problem, has the potassium nitrate being mixed in as the solute and the water as the solvent. onto calculating moles for the solute. There are 6.07 grams of potassium nitrate, and they need to be converted into moles. The conversion factor is a formula weight, 101.10 grams per mole, with an orientation that allows grams of potassium nitrate to cancel out. The math will produce 0.00600 moles of potassium nitrate. The two zeros after the 6 are significant figures. Step 2 has us get the volume of solution into liters. Like the previous problem, the volume is given in milliliters. And like the previous problem, it uses a metric conversion with an orientation that allows mils to cancel. The math produces 0.240 liters. By inspection of this calculation, we can reason out that moving from mils to liters is moving 3 decimal places to the left. We finish up by dividing the mole value obtained in step 1 by the volume value obtained in step 2. 0.00600 moles of potassium nitrate divided by 0.240 liters of solution gives a molar concentration of 0.0250 molar. That's the number value. The molarity has 3 significant figures, as does the numerical values in the problem. Staying with molarity, but moving into conversion factors. Molarity can be used to move between moles of solute and volume of solution. Molarity, as defined, has 3 variables. Given values for 2 of the variables, the third can be solved for. As a demonstration of the principle, consider the arrangement of units under the heading of current units, as in have or given units, and desired units, as in wanted or asked for units. The conversion that begins with liters of solution and ends with moles of solute requires a solution molarity in the orientation that allows the units of liters to cancel out, leaving the desired units of moles of solute. The 2 given values are volume of solution and the molarity. The third value, moles of solute, is solved for. Flipping the arrangement around so that the moles of solute are the current unit and the liters of solution are the desired unit will still require molarity as the conversion factor, but with moles of solute in the denominator so that units cancel out, leaving desired units of liters of solution. The 2 given values are moles of solute and the molarity. The third value, volume of solution, is solved for. These principles are very much like the principles that underline molecular weight as a conversion factor between grams and moles of a compound. Let's see these principles in work. How many moles of nitric acid, HNO3, are present in 0.250 liters of 0.75 molar HNO3 solution? Is this a conversion problem? Well, we should take our time and consider the problem first. We can do that with a setup to find the known and the unknowns. Looking at the problem, it can be seen that given is 0.25 liters of the acid solution. Make a note of that. And that the solution has a molarity of 0.75. Make a note of that. What the question asks for is moles of nitric acid. That is an unknown. The relationship between these values is current or given units of 0.250 liters and desired or wanted units of moles of nitric acid. This is indeed a conversion problem. It is a conversion problem of one aspect of the solution into another. The question to ask is, what conversion factor relates the volume of a solution to the moles of a solute? It is the molarity. But written in this form with capital M, it is not that helpful. It looks and feels more like a conversion factor when written in its definition form. 0.75 molar nitric acid is 0.75 moles of nitric acid per 1 liter of solution. Fortunately, this orientation is the correct one for canceling liter units out and leaving mole units. some calculator math, and 0.250 liters of a 0.75 molar nitric acid solution is shown to contain 0.1875 moles of nitric acid. A quick check of sig figs has us trimming that value down to 2 significant figures. Okay, to expand on problem solving using molarity, we will keep this same problem but insert a minor alteration to one of the values in the problem. Say that instead of 0.250 liters of solution, the problem gave 250 mils of the solution. This is an expansion because the volume units in molarity are in liters and not mils. But we've come across this issue before when calculating molarity. There we converted our mils of solution into liters of solution. The metric conversion factor is used, units cancel out, and the conversion into 0.250 liters is done. The amount of 250 mils was selected because the converted value fits right into the earlier solution. So the only real change with this new value is an additional conversion before the molarity conversion. Can the two conversions be combined into one-dimensional analysis equation? Of course they can. Convert the starting current units of 250 mils into liters with the metric conversion factor. Verify that units of mils cancel out, leaving units of liters. Convert those units into moles of solute with the molarity written in definition form. Verify that unit liters cancel out, leaving unit moles, and then do the math. The same 0.19 moles of nitric acid should come out. A second problem is probably in order. 0.10 moles of sulfuric acid, H2SO4, makes how many liters of 0.050 molar H2SO4 solution? As with the previous problem, a setup that searches the problem for knowns and unknowns is a helpful step. In this problem, the given is 0.10 moles of the solute sulfuric acid, and the concentration is 0.050 molar sulfuric acid. The unknown in this question is the liters of solution. The relationship between these values is the given or current units of the 0.10 moles of sulfuric acid and desired or wanted units of liters of solution. Yes, we have another conversion problem. Given this relationship, what is the conversion factor that should be inserted between the moles of solute and the unknown volume of solution? It is the molarity. Does this orientation of molarity allow for the canceling out of units of moles? No, it doesn't. It will be necessary to flip the orientation so that the moles are in the denominator, which does allow canceling of moles and leaves the desired units of liters. Doing the math produces a value of 2.0 liters to 2 sig figs. This is the core of a mole to volume conversion using molarity. Such problems can be a bit more complicated though. For example, the moles of sulfuric acid could be given as grams of sulfuric acid. Essentially, this is the same problem with an additional step. What is that step? Well, molarity can only convert between moles and volume, so the gram value is going to have to be converted into moles. There will be two conversions in this problem if grams are given instead of moles. What is the conversion factor that allows grams to be converted into moles? It is the molecular weight of the acid. 98.1 grams of sulfuric acid is 1 mole of sulfuric acid. Is this orientation of the molecular weight correct for the conversion? No, it isn't. Grams need to cancel out, so the denominator of the conversion factor has to have grams of sulfuric acid. The molecular weight needs to be flipped. Now grams can cancel out, and the math yields 0.10 moles of sulfuric acid, just like the value in the original problem. This calculated mole value can be inserted into the core solution given the requested value of 2.0 liters. These two conversions can be combined into a single dimensional analysis equation. The given or starting or current units in this problem are the grams of sulfuric acid, which need to be converted into moles. Insert the first conversion factor, the flipped molecular weight, and cross out gram units. That leaves moles, which the second conversion tells us uses the flip of the molarity as a conversion factor. Verify that the unit moles cancel out, get the calculator, and punch a final value of 2.0 liters. This modified example 2 is a very common homework molarity problem. The next concentration scale we are covering is molality. It is not a common scale, but its usefulness can be seen with the limitations of the scale we just covered, molarity. Yes, it's very easy to confuse these two names. They only differ by one letter. Nevertheless, the problem with molarity is that the volume can be temperature sensitive. That is, many solutions expand with increasing temperature. Volume gets larger. If volume increases with temperature, the denominator of the fraction gets larger, making the overall fraction smaller. That means molarity decreases. And this is so even though the same mass of solute and solvent are used. The amount of matter does not change, but the concentration does. That makes molarity a less than optimal concentration scale for some processes, especially those processes that are accompanied by a temperature change. Consider molality. It is the number of moles of solute per kilogram of solvent, moles per kilogram. Importantly, the mass of the solvent is not temperature sensitive. Molality does not vary with temperature like molarity does. This makes molality the optimum concentration scale for some processes, especially those that are accompanied by a temperature change. It is also called molal concentration. Molal is used with molality like molar is used with molarity. Molality is used when dealing with colligative properties. Such properties include boiling point elevation and freezing point depression. Colligative properties are covered in their own lecture in the water and solution series. In that lecture, being able to calculate molalities is an expectation, which is convenient since that is our next topic. Calculating molality is very similar to calculating molarity. Begin by calculating moles of solute. Convert mass values of solute into moles. Then get the mass or weight of the solvent, and that needs to be in kilograms. Solvents are usually measured by volume, so some sort of conversion will probably be necessary. A convenient relationship exists between the weight and volume of water, which is the most common solvent found in our studies. Between the temperatures of 4 degrees and 40 degrees Celsius, to two significant figures, 1.0 kilograms of water is equal to 1.0 liters of water. That allows the following conversion factors. Moving between weight and volume of water in this temperature range is very straightforward. The last step is to take the moles of solute from step 1 and divide them by the kilograms of solvent in step 2. Two examples will help solidify the process. The first example asks if 87.7 grams of sodium chloride, NaCl, is added to 0.500 kilograms of water, what is the molality of the solution? Step 1 in getting molality is to get moles of solute. That requires a recognition of the solute in the solvent in the solution. NaCl is the solute. A salt is added and dissolved in water, the solvent. The solute is given as 87.7 grams. The objective is to convert that into moles. The conversion factor is the formula weight of NaCl, 58.44 grams per mole. Note that the formula weight is oriented so that grams are in the denominator, allowing units to cancel. 87.7 divided by 58.44 is 1.50. There are 1.50 moles of sodium chloride in 87.7 grams of sodium chloride. Now, getting the weight of the solvent. Conveniently, the weight is already given in kilograms, 0.500 kilograms. It is in the correct units, so there is nothing more to do in this step. Molality is gotten by dividing the moles of solute from step 1 by the kilograms of solvent in step 2. 1.50 moles of NaCl divided by 0.500 kilograms of water, giving a molal of 3.00. Not too bad. This is the core of a molality calculation. Variation to this calculation include the solvent being given in units of volume. Liquids are usually measured by volume, so more often than not, this is the unit presented. The challenge to the core calculation will be in step 2, getting the weight of the solvent. Now, the starting value here is the volume of water. As was discussed when outlining these rules, there's a straightforward conversion of liters of water to kilograms of water. That did come with a temperature range caveat. The temperature of the solvent needs to be included to make this conversion. Now, units can be canceled and a final value obtained. The 0.500 kilograms of water is the same value the problem originally provided. So the step 3 calculation is the same, with the same 3.00 molal answer. A second example says that a 4.5 gram sugar cube, sucrose, C12H12O11, is dissolved in 350 ml of lemonade at 4 degrees Celsius. What is the molality of the sweetened lemonade? Begin by getting the moles of solute. A review of the problem shows that sugar to be the solute. It is getting dissolved, and the lemonade as the solvent. Sugar is given a mass of 4.5 grams, and that needs to be converted into moles. The molecular weight of sucrose is given in the problem as 342.2 grams per mole. The orientation of the molecular weight is such that grams cancel out. The division of 4.5 by 342.2 gives a mole value of 0.0132. In this problem, that is the easy part. A bit more difficult is getting the weight of the solvent. It is given in mils, so a conversion into kilograms is necessary. Is there a convenient volume to mass conversion for lemonade? Not really. But lemonade is mostly water, and the other component, lemon juice, is also mostly water. Given that, we will say that volume of very dilute solutions is almost equal to volume of the solvent. It will not be too big of a stretch to consider the lemonade as essentially all water, which does have a nice conversion. There are temperature constraints to this conversion, and a check of the problem shows that the conversion is acceptable to 2 significant figures. A second issue with 350 mils is that the conversion factor uses liters as its volume units, not mils. Is there a conversion factor that gets mils into liters? Yes, the standard metric conversion. These 2 conversions can be done in separate steps or in a dimensional analysis equation as shown here. Canceling liters leaves kilogram units, and a bit of math gets the mass of a lemonade as 0.35 kilograms to 2 significant figures. The molality calculation is moles of solute from step 1 divided by kilograms of solvent in step 2, 0.0132 moles of sucrose divided by 0.35 kilograms of water or lemonade. That gives a solution of 0.377 molal sugar. Notice, however, that the given solute mass is to 2 significant figures. The final answer must also be limited to 2 sig figs. The molality is 0.38. Molality can be used to move between moles of the solute and the mass, kilograms, of solvent, much in the same manner as molarity allowed the conversion between moles of solute and liters of solution. Using the same headings of current units and desired units, conversion between kilograms of solvent and moles of solute requires a molality in an orientation that has kilogram units cancel out, leaving the desired units of moles of solute. Flipping that current and desired units around gives an arrangement where moles of solute are converted into kilograms of solvent. A flip of the molality is the conversion factor here, since units of moles of solute cancel out, leaving the desired units of kilograms of solvent. An example problem will emphasize just how similar these principles are to those used with molarity and molecular weight conversions. The example asks, how many kilograms of water is needed to make 1.50 molal solution from 0.500 moles of potassium chloride, KCl? To be sure that this is a conversion problem, a review of the problem is in order. Known from the problem is the amount of potassium chloride in moles. Also known is the molality of the solution. It is 1.50 molal. What is unknown is the kilograms of solvent in the solution. The between known and unknown is current units of 0.500 moles of potassium chloride and desired kilograms of solvent. Clearly a conversion problem. The other known quantity from the setup is the molal, and it will serve as the conversion factor. However, the orientation as written, 1.50 moles of potassium chloride over 1 kilogram of water, is not correct. The current unit of moles does not cancel out. That is an easy fix though. Flip the orientation, and the mole units cancel out, leaving units of kilogram. Some calculator work, and 0.500 moles of potassium chloride dissolve in 0.333 kilograms of water, and that will make a 1.50 molal solution. This is a core molal conversion. A modification to this strategy would occur if the question asked not for kilograms of water, but the much more common unit of liters of water. Since volume is temperature sensitive, a temperature needs to be given. Here it is given as 22 degrees Celsius, which falls within the temperature range that allows the kilograms of water to liters of water conversion we used earlier, which means we can use it again. The core conversion gives kilograms of water, and that is the starting value for the second conversion, kilograms to liters. The conversion factor needed here will have the current unit kilogram in the denominator and the desired units of liters in the numerator. Starting units cancel, and a very simple math step gives the final answer of 0.33 liters of water. The 2 significant figure answer comes from the 2 sig fig limit of the kilogram to liter conversion. For completion's sake, we should combine these 2 conversions into a single dimensional analysis equation. It starts with the original given value of moles of potassium chloride and aims at the final value or desired units of liters of water. Like the equation below, the starting unit of moles will be converted into the units of kilograms of water with a flip of the given molal, as validated by the moles canceling out. The new current unit of kilograms of water will be converted into liters of water with the conversion factor of the above equation. Multiplying all the numerators together and dividing all the denominators will produce that same value of 0.33 liters of water. The logic of conversions are essentially the same. The more we see of them, the more the logic sinks in. The third mole-based concentration scale is the mole fraction. It is the ratio of moles of one compound to the total number of moles of the solution or mixture. It is given the symbol chi, which is a lowercase Greek letter, and like all fractions, is the ratio of part to whole. The values in this fraction, however, are strictly moles. If we consider a mixture that just contains substance A and substance B, the mole fraction of A is moles of A over moles of A plus moles of B. That might be easier to follow in fraction form. The part, moles of A, over the whole, moles of A and moles of B. Additionally, the mole fraction of B is moles of B over moles of A plus moles of B. the part moles of B over the whole moles of A plus moles of B. Because the sum of the parts must equal the whole, the mole fraction of A plus the mole fraction of B equals 1. Mathematically, that can be shown by putting the mole fractions in fraction form, and since these two fractions have the same denominator, add the numerators and keep the denominator. It follows that if numerator and denominator have the same value, the fraction is 1. Anything divided by itself is 1. Mole fraction of A plus mole fraction of B is 1. This equation tells us that if we know one of the two mole fractions, we can calculate the other. If we subtract the term mole fraction B from both sides, we get a new equation solved for mole fraction of A. An equation that is solved for mole fraction of B is obtained in a similar manner. These are very useful equations in two-part mixtures. Many students may never be faced with a mole fraction situation that has more than two parts. But just so that we know, for mixtures with 3 or more parts, the statement that the sum of the parts equals the whole still holds. And shown here is the generic mathematical equation that accompanies that statement. On the left are all the mole fractions for any number of parts. And on the right is the sum of 1. The mole fraction for any one part can be isolated mathematically by subtracting all the other parts from both sides. This is just an expansion of how we generated the two equations at the bottom of the screen. A specific and common example of mole fractions involves solutions that are made of a single solute, substance A, and a solvent, substance B. The mole fraction of the solute is the moles of solute over moles of solute plus moles of solvent. The mole fraction of the solvent is moles of solvent over moles of solute plus moles of solvent. The mole fraction of the solute plus the mole fraction of the solvent will be equal to 1. Sum of the parts still equals the whole. Mole fractions are used for specific purposes like dealing with partial pressures of gas. Actually calculating mole fractions is not that involved. Mole fractions can be determined in a 3-step process. Start by calculating the moles for all components in the mixture or solution. This will usually involve the formula weight of the compounds as conversion factors. From there, get the total number of moles by summing all the moles calculated in step 1. That is the whole in the fraction. To get the mole fraction of interest, that is of any one substance, divide moles of interest, step 1, by total moles, step 2. Once the moles have been determined in step 1, the rest of the process is basic arithmetic. A couple examples will prove that. First example, 333.0 grams of water is needed to make a 1.50 molal solution from 0.500 moles of potassium chloride. What is the mole fraction of the potassium chloride? What is the mole fraction of the water? This problem can be considered a follow-up question to the example problem covered in molality as a conversion factor, since it uses the same compounds and the same values. Beginning with the potassium chloride's mole fraction, but sharing the first two steps with water's mole fraction. Calculate the moles for all components. The potassium chloride was nicely provided in mole form, so that compound is set. The 333.0 grams of water will need to be converted into moles of water. What do we use to complete this conversion? It is the molecular weight of water, 18.02 grams per mole. The orientation of molecular weight is such that grams of water cancel out. Doing the division math gets 18.48 moles of H2O. Step 1 is done, and that is the bulk of the work. Step 2 is the arithmetic step of adding all the mole values together to get a whole. That is 0.500 moles of KCl plus 18.48 grams of H2O. A good way to get the number of significant figures correct is to line up the decimal points and note the last digit of significance. The sum is 18.98 moles. Clearly there is much more water than potassium chloride, and we should expect the respective mole fractions to show that great difference. To get the mole fraction of the compound of interest, potassium chloride, take the moles of potassium chloride and divide them by the total moles from step 2. Part divided by the whole. The math comes to 0.0263. The mole fraction is usually given as a decimal. We'll keep track of that value as we move to the second part of the question, the mole fraction of water. The nice part about this calculation is that steps 1 and 2 are identical to those for Chai KCl. All that is left to do is to divide the moles of interest by the total moles. That is 18.48 moles of water divided by 18.98 total moles. The fraction looks like it's pretty close to 1, and it is 0.9737. Let's keep track of that value and double check our answer. Earlier it was said that the mole fraction of the solute plus the mole fraction of the solvent should equal 1. If we did our calculations correctly, then 0.0263 plus 0.9737 should be equal to or close to 1. And it is. The parts sum to the whole. There is another way to come up with the mole fraction of water after we calculated the mole fraction of potassium chloride. It starts with the summation equation and then algebraically solves for the mole fraction of the solvent. The resultant equation has the calculated value on the right-hand side of the equation. Plugging those values in and solving the math gives the same value as was calculated using the 3-step process. Both ways work if the math is done right. Circumstance will show which is easier. Our final example says that a solution contains 10.0 grams of pentane, C5H12, 10 grams of hexane, C6H14, and 10.0 grams of benzene, C6H6. We are asked to find the mole fraction of pentane. The first thing to note is that there are 3 substances, all liquids, in this equation. It is still solved the same way as the previous 2-substance example. Our first task, and the one that involves the most work, is to get the mole values for all components or substances, beginning with the 10.0 grams of pentane. To speed matters along, the molecular weights of the organic liquids will be provided. The molecular weight of pentane is 72.15 grams per mole. The orientation of the molecular weight has the current units of grams in the denominator, so that the units cancel out. The division of the numbers produces 0.139 moles of pentane. The 10.0 grams of hexane are converted the same way. The molecular weight is 86.18 grams per mole of hexane. It's inserted such that grams cancel out, and a value of 0.116 moles of hexane is produced. The third substance, benzene, is converted into moles with a molecular weight of 78.11 grams per mole. 10 grams of benzene is 0.128 moles of benzene. The hard work of the problem is done, and nothing but arithmetic awaits us. Totaling the moles is addition. The values have been lined up on their decimal points, and each has the same number of significant figures. The sum, or total number of moles, is 0.383. Pentane is our substance of interest, and its mole fraction is calculated by getting its moles from step 1 and dividing that by the total number of moles, 0.383. The mole fraction of pentane in decimal form is 0.363. Is it correct? Well, the best way to verify the accuracy of the calculation is with the sum of mole fractions equals 1 equation. That would require us to determine the mole fractions of the other 2 organic liquids. Since it is relatively straightforward to calculate those mole fractions, once we had determined one of the mole fractions, we should do that. Let's keep track of this value and find the mole fraction of hexane. Steps 1 and 2 are identical, and getting the mole fraction of interest has us take the number of moles of hexane from step 1 and divide that by the total number of moles, 0.383. Hexane's mole fraction is 0.303. We'll save this value and move on to the calculation of the mole fraction of benzene. Again, there's no need to repeat steps 1 and steps 2. The mole fraction of benzene has the moles of benzene divided by the total number of moles for a decimal value of 0.334. Adding that value to the other mole fractions puts us in the position to verify whether or not we have correctly calculated the mole fraction for these three organic liquids. Returning to the sum of the parts equation, we see that adding the three mole fractions together should get a value of 1, or very close to that. This result lends great confidence that the mole fraction of pentane was correctly determined. That ends our coverage of concentrations containing mole values. Recapping the lecture, some compounds dissolve in liquids and form solutions. The dissolved compound is called the solute. The dissolving liquid is called the solvent. More detail is provided on solutes and solvents in the solution and solubility lecture. The first of the three concentration scales involving moles is molarity, capital M. It is the number of moles of solute dissolved in 1 liter of solution, moles per liter. Molarity is also called molar and is a very important scale in chemistry. As a conversion factor, molarity can be used to move between moles of solute and volume of solution. One of the limitations of molarity is that volume can be temperature sensitive. That is, the molarity can change with temperature. That is not the case for the second concentration scale, molality, lowercase m. It is the number of moles of solute per kilogram of solvent, moles per kilogram. Both the numerator and the denominator are based on weight, which is not temperature sensitive. Molality is also called molal concentration. Molality is used when dealing with colligative properties. The third concentration scale is called the mole fraction. It is the moles of solute over total moles of solution or mixture. It is given the lowercase Greek letter chi as a symbol. Since it is a fraction, it follows the sum of all parts equals the whole. That means adding all the mole fractions together has to equal 1. And that concludes our lecture. While we covered 3 concentration scales, molarity is the most important scale used in chemistry, and that one should get your focus.